All right, let's do some examples now and see if you understand how to graph rational functions. So here's a function. It's a parabolic function, and we want you to figure out what would be the graph of its reciprocal function. We've color-coded it so you can see that the blue parts are where the function is positive, red part is where the function is negative. X equals -2 and x equals 1 is your x-intercepts. Pause the video, see what you can do. We did similar examples when we were doing reciprocal functions. So here, x equals -2 and x equals 1 are places where the function is 0. So 1 over f of x is going to have those as your vertical asymptotes. When x goes to infinity, function goes to infinity. When x goes to -infinity, function goes to infinity, which means 1 over the function will have y equals 0 as your horizontal asymptote. And so once we have the asymptotes, we also know that between -2 and 1, function is negative. So 1 over f of x will be also negative in that interval. When x is less than -2 or greater than 1, function is positive. So 1 over the function will also be positive. So that means we can sketch the graph now as x goes to infinity, y equals 0 is asymptote, and the function is positive. So it's above the x-axis. And then from the left-hand side, positive and getting close to 0 for f of x means positive and shooting to infinity for 1 over f of x, and so on. Verify and make sure you understand what just happened. All right, try this on your own. Find the reciprocal function graph here. What you can see is that x equals -3 and x equals 2 are your x-intercepts for f of x. So x equals -3 and 2 will be your vertical asymptotes. And again, when x shoots to infinity or -infinity, your graph is going to -infinity, which means 1 over f of x will go to 0. So 0 will be your horizontal asymptote. Here you can see 1 over about 6. So a 6. And so it will be like somewhere here. And then the remaining graph comes from looking at this curve here. Close to 2 from the left-hand side, graph is positive, getting close to 0. So positive and shooting to infinity. As x goes to 2 from the right-hand side, it's getting closer and closer to 0. But from the negative side, which means that graph is shooting to -infinity, close to 2. As x goes to positive infinity, graph is going to -infinity for f of x, which means negative. So that means underneath 0, going towards 0 when x goes to infinity for 1 over f of x. And similarly on the left-hand side. So blowing up still keeps positive terms positive in 1 over f of x. Negative terms remain negative. All right, go ahead and see what the graph of the reciprocal function of this graph would look like. You can see it's almost like a periodic function, like a sound wave or a light wave. It's reciprocal function. Go ahead and sketch the graph. All places where its x-intercepts are, you're going to have vertical asymptotes. They're all y coordinates are either 1 or -1. So wherever you have 1, between 0 and 2, between 0 and 2, you have a 1. 1 over 1 is 1. And blew up means it's got inverted. On the other hand, you have a -1 and inverted, and so on, up and down, up and down. All right, let's take a look at the function f of x, which is x minus 1 squared times x plus 1 cubed. You already know that from graphing of polynomial functions at -3 and 1 are x-intercepts. And at -3, you have a cubic. And at 1, you have a parabolic function. X squared times x to the third is x to the fifth. So left hand is down, right hand is up because it behaves like x to the fifth or odd degree power function. So there's your function for polynomial x minus 1 squared times x plus 3 cubed. So now what happens if instead of 1 as leading coefficient, I put a 2 in front? Well, then it's this graph over here, this second graph that you see, which is basically taking the original graph and stretching it by a factor of 2. What if you take the original graph and times it by a half? Then it will vertically compress it. If you put a negative 2 in front, it will reflect and stretch by a factor of 2. These are the things that we saw in graphing polynomial functions. A natural question a mathematician would want to ask is, what if instead of multiplying by, say, a half, I multiply by 1 over x, a variable stretch factor? Then what happens? We would expect a similar behavior of compression, but with a different magnitude at every single x coordinate. On top of it, the x in the denominator will cause us a vertical asymptote. So here's our graph, x minus 1 squared and x plus 3 cubed. And if you multiply by 1 over x, which is the same as division by x, at x equals 0, you will have a vertical asymptote. But if you look very carefully, this graph preserves the cubic aspect at x equals negative 3. And at x equals 1, it preserves the parabolic nature of the original polynomial function. So the question, what properties of the numerator function are preserved, is answered here. As long as the denominator does not override the numerator power, which means denominator power is smaller than numerator power, the basic shapes from the numerator polynomial is preserved. Because we're dividing by x, when x is negative, negative divided by negative will make it positive. That's why instead of the graph being underneath x-axis below negative 3 for x, you have x equals negative 3, and below the graph is now positive because it got reflected across the x-axis. Similarly, all positive terms became negative between negative 3 and 0 because you are dividing by a negative number. Positive number divided by a negative number will give you negative number. However, when x is bigger than 0, all positive terms, so if you're dividing positive numbers by positive numbers, you will remain positive. So that's why the parabolic nature remains exactly how it was, except that when x goes to 0 from the right-hand side, the graph will shoot to infinity. So what happens if instead of x, we divide by x squared? X squared is a positive term, which means some number divided by positive number is not going to change its sign. So you can see it preserves the basic shape, except that at x equals 0, the graph blew up or went to infinity from both left and right-hand side. And again, the power of the numerator is higher than the power of the denominator. And so really, the numerator power rules. And so numerator polynomials basic shape remains almost identical, except for the denominator, making you get a vertical asymptote. OK, so another question to ask then would be, what do we do here? If you divide by something other than x, like x minus 2 times x plus 1, again, the denominator still has lesser power than the numerator. So numerator, cubic behavior, and parabolic behavior should be almost identical to the previous polynomial. However, x equals 2 and negative 1 are going to create vertical asymptotes. And then when x is below negative 3, you have the denominator is all negative, negative, so positive, which means dividing by a positive number is not going to change the shape. So it's still going down. And then you have the shape here is going up between negative 3 and negative 1, which is where you have an asymptote. And so it's going up towards positive infinity from the left of negative 1. And if you look between negative 1 and 0, you have the graph is shooting towards negative infinity because you are dividing by negative numbers, so all positive terms became negative. And so that happens all the way until 2. And then after 2, it's all positive, so it's all going up again. But you can see that at x equals 1, you still have a parabolic behavior. At x equals -3, you still have a degree 3 behavior. So denominator set to 0 give you vertical asymptote. So here's the original function. And if you divide by x, then you can see it preserves the basic cubic and square function. Same thing here. All right, here we can look at the same example, dividing by x or x squared in a different light. If you do long division, this is what you'll see. So this polynomial here is the red dotted polynomial. So as x goes to infinity, you can see our graph gets closer and closer to it. This is called an asymptotic curve. Same thing when you divide by x squared. This polynomial you see here, which is the quotient, is going to be our asymptotic curve. So as x goes to infinity or negative infinity, the red dotted curve is what the original function f of x, which is the quotient of x minus 1 squared, x plus 3 cubed over x squared, or x minus 1 squared over x plus 3 cubed over x behaves like. You can verify that yourself by playing in Desmos. What happens to the numerator polynomial compared to the denominator polynomial? If you look at this polynomial divided by x plus 1, x minus 2, and you do long division, you will end up with this as your quotient, which is this dotted graph that you see here. And again, you can see that that is your asymptotic curve. So this gives us a sense of how we would go about graphing all rational functions. We can write them in factored numerator, factored denominator. That gives us the denominator set to 0 gives us vertical asymptotes. Numerator set to 0 gives us the x-intercepts. When you do long division, the quotient gives you the other asymptotes. And the remainder set to 0 will give you where the function intersects the asymptotes, the slant or oblique asymptotes or the asymptotic curve. All right, let's start out with graphing rational functions then. You're going to find x-intercepts, y-intercepts, vertical asymptotes, oblique or horizontal asymptotes, or asymptotic curves, and then points where the function intersects these other asymptotes. Please draw your asymptotes either as dotted lines or dotted curves, and use colored pencils to distinguish between different parts of your graph. All right, the first function is f of x equals 1 over x plus 2. We will do first 1 or 2 together so that you understand the steps. Step 1 is finding x-intercepts. Set numerator to 0 when the function is written as a rational function, numerator over denominator function. This case, the numerator is a constant, so it's never 0, so it has no solutions or no x-intercepts. To find y-intercepts, set x to 0, which gives us 1 over 0 plus 2, or 1/2. So 0, 1/2 is our y-intercept. Vertical asymptote, set the denominator to 0, which will give you x equals -2. To find the other asymptotes, you already can see that this is, when you do long division, written as 0 plus 1/2. So 0 is a constant, so y equals 0 is horizontal asymptote here, because our numerator degree is smaller than denominator degree. The remainder here is 1. If you set the remainder to 0, which in this case was 1, then you get 1 equals 0. So there are no points of intersection. You can also make a little chart of points, 2 points on the left and 2 points on the right of the vertical asymptote, just so you have a good rough sketch. And so plotting those coordinates will give you this graph right here. And we should have expected it to be the same as original shape power function of 1 over x shifted 2 to the left. So you can see how we make these connections between what you did in a previous section and this new problem. All right, so in this problem, you have 3x squared plus 3x minus 18 over x plus 1. So if you factor, you will see it's 3 times x minus 2, x plus 3. Setting it to 0 gives us negative 3 and 2 as our intercepts, x-intercepts. Setting y to 0, 0, negative 18 is our y-intercept. Denominator is x plus 1. Setting it to 0 gives us negative 1. So x equals negative 1 is our vertical asymptote. To get the other asymptotes, we'll have to take this and do long division. So let's go ahead and do that. So we have x plus 1. We have our numerator. We do long division. So times 3x. X times 3x is 3x squared. X times 1, 3x times 1 is 3x. When you do subtraction, you will end up with negative 18. So we have y equals 3x is going to be our oblique asymptote. And 18 is the remainder. 18 set to 0 means there are no intercepts between the oblique asymptote y equals 3x and the original function. Again, putting in coordinates 2 points on the left and 2 points on the right of the vertical asymptote and making a table, plotting points, will give us this shape that you see right there. All right, it's time for you to do problem on your own now. So consider this problem 2x squared plus 1 over x minus 2, x plus 3. So you are given this polynomial over polynomial, a rational function. Go ahead, pause the video here, find x-intercepts, y-intercepts, vertical asymptotes, do long division to find the other asymptotes. Go ahead, we'll wait until you're done. This might take you a while, so just pause the video here and then come back, please. It's extremely important you try this problem on your own, please. Are you waiting for me? Are you done? You couldn't have done it so fast, did you? You're stuck? If you are stuck, just remember, setting numerator to 0 gives you x-intercepts. Putting in 0 for x gives you y-intercepts. Setting denominator to 0 will give you vertical asymptotes. And then doing long division will give you the other asymptotes. And then plot points 2 on either side of all the asymptotes, the vertical asymptotes. Go ahead. I just reviewed the steps for you, so just give it a try. It's okay to be stuck. Just try it anyway. Go ahead. All right, assuming you've come back from pausing the video, our numerator is 2x squared plus 1 equals 0. Setting it to 0 gives us 2x squared equals negative 1. X squared is always positive, so there are no solutions, which means we have no x-intercepts. Setting x to 0 gives us negative 1/6. So 0, negative 1/6 is our y-intercept. Setting denominator to 0 gives us x equals 2 and x equals negative 3 as our vertical asymptotes. Let's do long division. All right, let's do long division. So we have x squared plus x minus 6, 2x squared. There is no x term, so we'll put a placeholder there, 0x plus 1. And then 2 times x squared is 2x squared. So 2 times x squared, 2x squared, 2 times x, 2x, 2 times negative 6, negative 12. Do the subtraction. 0x minus 2x is negative 2x. 1 minus minus 12 will give you 13. And this is less degree than x squared plus x minus 6. So that is our remainder. So we have 2 plus negative 2x plus 13. So y equals 2. So y equals 2 is our horizontal asymptote. Again, if you take negative 2x plus 13 equals 0, 13 halves is where your graph will intersect the horizontal asymptote of y equals 2. So setting the remainder to 0 gives us 13 halves and 2 as a point on the horizontal asymptote. So you go ahead and make a table for these values of x coordinates. So then our graph will look like this. You can see here is the point where it intersects I've blown it up a little just so you can see what is happening there.